So moving on to our next type of reaction, we're going to have predicting acid-base reactions. So that's what's coming up next. So we refer to this as a neutralization reaction. So what we're going to do is we're going to combine an acid and a base, and our products are always going to be salt and water. Okay, so of course your salt then will be an ionic compound, and it's going to be the ionic compound that's formed from the neutralization reaction. So we looked at double displacement reactions. These are very similar to those, except you know you're going to have a salt and a water as your products. Okay, so an example would be something like HClO4. That's our acid. We're going to react that with sodium hydroxide, our base. We're going to form that sodium salt, and of course our water molecule. Okay, so again, predicting these, you can just simply view them as the metathesis reaction, that double replacement. We can see here, if we write it out as an ionic form, we have our H plus with our acid, and it's going to combine with our OH minus of our base. That's going to give us our water, and that's going to be the driving force. Everything else is going to cancel out because the sodium perchlorate, of course, while it is a salt, we would have to dehydrate the reaction in order to capture that salt. That is a soluble salt. And so your net ionic reaction, you're literally just making water. Now that won't always be the case. Some acid-base reactions will give you a precipitate, but you'll just follow your solubility rules. Right? So it's only going to be once in a while that that's going to happen. Neutralization between a strong acid and strong base. Your molecular equation, something like this, we have a strong acid, HCl, strong base. Remember, it's a group 2A metal, so it's calcium. When they mix together, we're going to form two waters, and of course our calcium chloride will be aqueous. So again, your ionic equation written out would be 2H plus. We're just going to carry those coefficients just like we did before when we were working on just the net ionic equations. And then of course we'll cancel out any ions that are in solution, which will leave us again our water as our net ionic reaction. Now here we'll also have to do a little bit of work where we're going to have to cancel out those 2's, and so we'll get a 1-to-1 reaction. Okay. Now this is going to be true for any of our strong acids. So our strong acids and strong bases all are going to create soluble salts. No way around that. Okay. Now for a weak acid with a strong base, it's going to change up a little bit. We'll have our molecular equation where we're going to put our weak acid into solution. We're going to have our strong base, and we're going to form water and then our salt. All right. Now when we break apart the ionic equation, remember, some of this is going to stay in solution as a molecule. Okay, and that's going to be the big change. But if we use our net ionic reaction to cancel everything else out, then we're going to see what's going to fall out of this is we're going to have our acid, our weak acid. We're going to have our base react with that to form some water, but it's also going to leave us some of that conjugate base as well, that C2H3, that acetate. Okay. Now, strong acid with an insoluble base. So if we have an insoluble hydroxide like magnesium hydroxide, if we add HCl to that, we're going to force that reaction to create water. The ionic equation then, we'll have that magnesium hydroxide as a solid now, because remember that's going to be insoluble. It's not going to dissolve into water. Then we'll have our 2H plus our Cl2, our Cl minus, well, two of those, which means we'll make a magnesium ion, some chloride ions, and water. Of course, the chlorides will cancel out. So our net ionic equation is going to show that base plus acid is going to give us a magnesium ion and a couple of waters. So again, you're just following your neutralization reaction just like an ionic reaction. So we're going to go through the ionic step and then the net ionic step. All right, so neutralization of a strong acid with an insoluble base. Okay, we'll take aluminum oxide. So now instead of using a hydroxide, now we're using the aluminum oxide. 6HCl, we're going to get 2 aluminum chlorides and 3 waters. For your ionic equation, again, your base won't break apart here. We're going to have our acids, our chlorides. Now the aluminum chloride, of course, is soluble, and of course we're going to make molecular water. So for our net ionic equation, we're going to start to cancel out chlorines and leave everything else, and we'll just write that. All right, so strong acid with a weak base. So here we have our weak base ammonia plus a strong acid. It's going to make ammonium chloride aqueous. So our ionic equation here, we're going to take ammonia plus an H plus a Cl minus, and then we're going to make a salt, right? Your net ionic equation, we have the chlorides going out of solution, which will leave us ammonia plus the H plus will give us the NH4, the ammonium. All right. So what is the net ionic equation then for the reaction between the following reactants? So if I take HNO3 and I mix it, strong acid with a strong base, what would be the net ionic equation? So of course we'll break that into H plus NO3 minus plus calcium 2 plus hydroxide, or you can commit it to memory because we've already said strong acid plus strong base gives us water. H plus OH minus goes to water. All right, how about N2H4 plus HI? So now we have a strong acid. Is N2H4 going to be a strong base? Of course, that's not on our list. It's not on our list for being a strong base. All right, so here we're going to have the N2H4. It's molecular. It doesn't break apart. The HI does break apart. The I's will cancel out on the product side, and we end up with N2H5 with a plus charge. All right, how about H3 and H2 plus HC4H7O2? Again, now we have a molecular base with a weak acid. And so for this one, these will not ionize, they don't break apart. This one will, but some of that H plus is simply going to get eaten up, right? And so we're going to end up with CH3 and H3 plus the C4H7O2 with a minus. All right. So what is the net ionic equation for the reaction NaOH plus HF? Remember, HF is in group 7A, but it is not a strong acid, right? HF is our weak acid. And hopefully you came up with D. OH minus plus HF will produce that water plus F minus. All right. What is the net ionic equation for the reaction NH3 plus CH3COOH? Okay. So now we have our weak base with a weak acid. Hopefully you've come up with D. NH3, of course, doesn't break apart. Our weak acid, that piece won't break apart. The H plus will end up with the NH4. Okay. All right, so what is the net ionic equation for the reaction of an insoluble hydroxide and a weak acid? So here's our magnesium hydroxide, which is insoluble. It's going to start off as a solid. And we're going to mix acetic acid with that. That's our weak acid. And hopefully you've come up with magnesium acetate plus 2 waters. The ionic equation will look like this. So you have magnesium hydroxide does not break apart. Your weak acid will not break apart. On the other side, we're going to make magnesium acetate, which will break apart. We'll need 2 acetates. So there's 2 is going to pop out there. And of course, we're going to make 2 waters. There are no spectator ions here. Okay, so nothing's going to cancel out. So in this case, your net ionic equation is going to be the same as your ionic equation. All right. Acid salts. Polyprotic acids can be neutralized stepwise. So we saw how they can dissociate stepwise. Now what we want to do is neutralize them stepwise. Now we can halt that neutralization then at each step. So the name must specify the number of hydrogens remaining in the salt. So our acid salts then. Your formula contains a cation, a hydrogen, and an anion. So the acid salt can react with a base. So if you're not sure what we're saying here, what we mean when we say an acid salt is if I think about a polyprotic acid, something like, say, H2SO4, and if you reflect back to an earlier segment, we showed how this can dissociate to give us H plus HSO4. Remember, this is going to be no charge. This is now a plus and a minus. And of course, then we can take this one and do another step where we get H plus SO4, whoops, horrible SO4, sorry about that, 2 minus, right? So we can take each hydrogen off stepwise. So here, what we're going to do is take H2SO4 and react it with a strong base. Now the first reaction then would have that potassium connecting to the HSO4. And that's what we call our acid salt. So now we took that HSO4, which can't really exist by itself, right? Now in solution it can, because it'd be hydrated, it'll have spheres of hydration around it. But if we're looking at it realistic, if we're going to stop the reaction, we're going to form one water, and then we're going to have this acid salt. So naming those acid salts. Remember, you have to tell you how many hydrogens are there and still attached to the anion, and they can be neutralized by additional base. So I can start with the acid salt, in this case Na2HPO4. Now remember, we removed 2 of the hydrogens off of the phosphoric acid. So to name that, we're going to call it sodium hydrogen phosphate. It's got 1 hydrogen on it. Sodium hydrogen phosphate. Now let's say I have 2 hydrogens on it. So now it's NaH2PO4. Well, here's where it can start to get a little confusing with your naming, because previously prefixes meant we had molecular compounds. But remember, when we're looking at polyatomics, the polyatomic piece typically is considered to be molecular. So we have sodium dihydrogen phosphate. Okay, sodium dihydrogen phosphate. So for KHSO4 then, what would we call that? Potassium hydrogen sulfate. Okay, so some acid salts have common names, so you got to watch out for that one as well. So we have NaHCO3. So what would I call this with our system we're looking at? Well, I'd call it sodium hydrogen carbonate. However, if I go in the lab, it's typically called sodium bicarbonate. Don't ask why, I don't know. This stuff started before I was born. So unfortunately, the common names, you just kind of have to know as you're working your way through the lab, or just recognize it, right? Because bicarbonate doesn't make any sense. When I think of bicarbonate, I think I have 2 carbonates, but there isn't 2 carbonates there. There's only 1 carbonate. So unless you see, I don't know, 2 carbonates on a different compound, you just have to remember bicarbonate is probably going to be a common name. Now, another thing we can do in our metathesis reactions, or double replacements, is form gases. Okay, so reactions involving certain ions will lead to the formation of a gas. So far we've seen that we're going to create either a water, an insoluble salt, and now we're going to see it could lead to the escape of gas. Okay, so once the gas escapes, it cannot redissolve. That means that's going to drive that reaction to completion. So as long as gas is evolving off the reaction will continue to go until you run out of materials. Many compounds that contain anions that give rise to gases are going to be insoluble. So adding an acid to these anions then will form a gas. One of the most common gases you're going to form is going to be hydrogen gas. And remember, hydrogen is diatomic, so that means H2 will be the gas coming off. Another one that's common is going to be CO2, carbon dioxide. You'll see carbon dioxide coming off. Typically, whenever you see a carbonate on the reactant side, CO2 is going to be a gas that can potentially evolve, right? So some common gases then are going to be CO2, SO2, and ammonia gas, NH3. So it'll come off as H2S, HCN, unstable compounds that can decompose to form that gas. So again, here's where we'll see that CO3 will give us H2O and CO2 gas. H2SO3, we're going to see that SO2 gas coming off. And of course, if you see ammonium, then you got to watch out for ammonia gas coming off. So the processes here that we're looking at is the CO3, hopefully you can see, will typically give us a CO2. An SO3 will give us an SO2. And whenever we see ammonium, we always have to be ready for the potential for ammonia to come off as a gas. Right? So reactions that release CO2 would be something like an acid with a bicarbonate. So there we have a sodium bicarb, NaHCO3. We'll mix that with a strong acid. We'll get sodium iodide as a salt coming off. It's aqueous. We'll produce water and CO2. Okay, so water and CO2. So acid with a carbonate. So if I just have a CO3, no HCO3, notice we'll still form the water and the CO2. Okay, so one of those oxygens is going to break off. Notice we have two equivalents of the hydrogen. That's where we're going to get our water. Okay. So acid with sulfites or bisulfites. There's that HSO3. All right, they'll typically going to give you SO2 gas. So here we see potassium sulfite giving us SO2 gas. Lithium bisulfite is going to give us SO2 gas. Acid with sulfides, again, you'll get the H2S. Okay, so we get another gas. Acid with cyanides will typically give you HCN as a gas. Bases with ammonium salts will release that ammonia as a gas. So these are just examples. I don't expect you to commit them to memory, but you do want to be, you might want to commit that piece to memory back here where we're looking at things to watch out for. So whenever we see a carbonate, you want to be ready for the CO2 gas. That kind of thing you probably do want to commit to memory. Okay. HCN, a common gas that's made along with the H2S. That's the stinky stuff right there. All right, so write the molecular, ionic, and net ionic equations for the reaction of lithium sulfite with formic acid. So for your molecular equation then, you'd start off with these two things. Give you an opportunity to pause, see how you do. And so of course here, we're going to see the lithium replacing the acidic hydrogen. Right, that acidic hydrogen is then going to help break that SO3 into SO2. Now that third oxygen that's there, right, is going to combine with the two hydrogens that are coming from here. And that is where the water is going to come from. Okay. Now for your ionic equation, you'd break this apart. You have lithium sulfite. There's the lithium sulfite. You have your organic acid here. And then of course, the lithium piece is going to break apart. So there's that with the lithium, your SO2 gas, and of course your water. Your lithiums are going to cancel out, and we'll be left with everything else that's there in the ionic equation. All right, what is the net ionic equation then for the reaction of HCl with KHCO3? So here are your options. Now if I were working this problem, I see that CO3, what should I expect for a gas evolution at this point? So I would be looking for CO2 gas. So which ones have CO2 gas? Does not. Does not. All right, does, and does. So I've got it limited down to C, D, and E. So just from that, now we know we also have to make water. All three of them have water. What's going to be the salt then? Well, the salt that could potentially come out of that is KCl. Okay, is that salt going to make it all the way through? Or is it going to get eliminated? So in this one, it says KCl is going to be aqueous. I don't know if I like that too much because that's a very soluble salt. All right, so did that K plus come off here and get canceled out there? This one shows K plus on both sides. So we know that that should have canceled out. So we know that D can't be the answer. So now we've eliminated A, B, D. Still not happy with C. I mean, this should break apart to H plus and Cl minus. This one should have broken apart to K plus and Cl minus. That makes me think the Cl minuses should cancel out. And of course, they should cancel out, which means my answer then is E. Hopefully you did well there. All right, what is the net ionic equation for the reaction of HBr with K2SO3? So hopefully you're going to use the same mental trick. All right, we see the SO3, that should flag right away. What gas will SO3 produce? Hopefully you recall that it's going to make SO2 gas. And so after you eliminate a few things, hopefully you come up with C. 2H plus SO3 goes to SO2 plus H2O. All right. So your metathesis overview, remember these are our double replacement reactions from yesterday's. So one, you can have a precipitation. You're going to have two solutions that are going to form a solid product. You could have a neutralization. Here we're going to have an acid and a base, and it's going to form a salt and water. You now can have gas formation. So the reaction then forms one of the following gas products. Okay? Or you could form a weak electrolyte, so one that's going to be a little less soluble. So you'll see a little bit of precipitate pop out. So a salt of weak acid reacts with acid to form a molecule itself. Okay? All right, so I think we'll pause this segment here, and we'll come back next looking at predicting the reactions and writing out the equations themselves. So at this point, I've kind of been working with you to show you different examples. Next, you're going to be able to predict these. So make sure you have your solubility rules for the next segment and be ready to take a look at how some of those things are going to form.